Okay, so the other thing I wanted to talk about this week was why we can see different phases of the moon at different times of the day. Now, I'm pretty sure you've all looked out and you've seen the moon, in the middle of the night, a nice big round full moon. But I can guarantee no one's ever seen that full moon out in the middle of the afternoon. You can't look up at noon and see the full moon. And on the same hand, I'd wager to bet that none of you guys have ever been able to look up in the middle of the night and see just a little tiny crescent moon lighting up the night sky. So there's good reasons for this, and it all goes back to the fact that, again, the moon orbits the Earth over the course of 1 month. So I wanted to diagram this out a little bit. I turned the brightness down so you could hopefully see the blackboard a little better here. But the first thing I want to show here is what's called the Earth clock. Okay, so the basic idea, I'm just going to randomly decide that the sun is going to be coming from the left here. So this is the sun. You can see that. And the sun is illuminating the Earth and the moon from the left-hand side. And then over here, I'm going to draw the Earth. Actually I'll make that quite a bit bigger. We're going to be looking at this from the top down. From the top-down view from above the solar system. So we're looking right down here. We're looking at the North Pole, and the Earth will be rotating around counterclockwise. So again, that's the North Pole there, and the whole Earth is we're looking down on it. So actually, this line that I've drawn, the surface that we're seeing at the very edge is in fact the equator. If we're looking down from the very top, we're seeing the equator here. Now, I'm just going to ignore the moon completely here, and I just want to be able to point out where on Earth you would experience, say, noontime, or midnight, or sunset, sunrise. So first of all, if the sun is right there, the sunlight is hitting the Earth most directly right there. So if we imagine that we've lined up, every single person on Earth is around the equator, going all the way around. The person who would say that's high noon, the person who would say it's exactly noon, is going to be the person who is standing right here. That's like a gigantic person. But the point is, this person right here will look up, and directly overhead, they're going to see the sun. So for them, that's what we define noon time to be. Solar noon is when you are on the side of the Earth that is directly facing the sun. So I'm going to add a notch here and say it's noon. You know what, I'm going to make this bigger so you can definitely see this here. So there's the Earth, there's the North Pole, it spins around this way, and the side that's directly facing the sun is the side that, one more try. Nice, big, smooth circle, very good, noon. Okay, sorry about that. So, now if the Earth is spinning around, how long does it take to make one full rotation? You guys should all know it's 24 hours. So, after 1/2 of a rotation, if it's noon for us, and if we just hit fast forward on this, that person who is standing there at noon, exactly 12 hours later, they're going to rotate exactly halfway around the Earth. So 12 hours after noon o'clock, that person is going to be standing right here. And as we all know, 12 hours after noon is exactly when we call midnight. By the way, it's not cutting that out, I just didn't write the rest of the word. So noon is directly facing the sun, midnight is facing exactly opposite the sun. Those are the two key positions here. Now halfway between noon and midnight, 12 p.m., 1 p.m., 2 p.m., 3 p.m., 4, 5, 6. Because the Earth is rotating counterclockwise, 6 p.m. would be the time that someone who is on, as we're looking at the bottom of the Earth, would say. So this is 6 p.m. Now, I'm not trying to actually draw like a normal clock. Obviously, this doesn't really make sense here. But someone who, it's noon, they wait a few hours longer, it's then going to become 6 p.m., exactly 1/4 of a rotation later. And then at 6 p.m., if you wait 6 more hours, the Earth is going to rotate 1 more quarter of the way around. So it's midnight, someone right there. Same thing, if we let this go another 6 hours, eventually it becomes 6 a.m. for someone who is at the very top of the Earth right here. And then 6 hours later, again, it's noon. So, we've just made the basic main 4 quadrants. We know when it's noon because the person's looking right at the sun. If someone says 6 p.m., we know they're looking down in this direction here. Now what we can do is just kind of divide each little quadrant in half. So now we have halfway between noon and 6 p.m., which is pretty obviously 3 p.m. Halfway between 6 p.m. and midnight is 9 p.m. Midnight to 6 a.m., halfway is 3 a.m. 6 a.m. to noon, 9 a.m. Okay. So we've now divided this into 8 sections, each one 3 hours long. And the thing to do at this point is simply just to add 2 more little tick marks. So 1 p.m., 2 p.m., 3 p.m., 4, 5, 6 p.m., 7, 8, 9 p.m., 10, 11, 12. And so you kind of get the point here. But the important thing is now, if you were to call anyone on the Earth up and they would tell you what time they're experiencing, you could tell exactly where they are along this diagram. Now, it's true not everyone's on the equator. But if someone's saying it's noon, that means that they're along that line stretching straight from right there all the way to the North Pole. Obviously, if we're at like 45-degree latitude, which is roughly Minneapolis, we're about halfway between there. So someone in Minneapolis is still directly facing the sun, except they're not seeing it quite as high overhead as someone on the equator. Or if it's 6 a.m. for someone in Florida, they're not going to be right on the equator, but they're going to be along that line. So someone in Florida might be standing right there. Either way, they're still along that line of longitude extending from the equator to the North Pole. So this is important here because this is basically just telling solar time. Now this, by the way, this is not exactly the time that we have. There are a couple problems with this. So the time that our watch says is noon, that might not be exactly true because, first of all, right now, we're experiencing daylight savings time. So what's noon for us, when our clock says it's noon, in fact, we've switched the whole thing around by an hour. So in the summer, we actually move everything back 1 hour so that we get 1 extra hour of daylight at the end of the day. So from here on out, I'm going to disregard the fact that we're under daylight savings time, and we're just going to assume that everyone in the entire world never experiences daylight savings. Again, we can just go back and correct that, just add 1 hour back on, and we're fine. Second thing, obviously, during some parts of the year, the sun is going to be up a little bit longer in the day, the sun is going to be up a little bit less long in the day. Based on the tilt of the Earth, this basic picture works, but when we start talking about sunrise and sunset times, I'm just going to be talking about an average. On average, over the course of the year, the sun is up exactly 12 hours. Obviously, in the summer, it's up longer than that. In the winter, it's up shorter than that. But when I talk about the length of the day or the moonrise and moonset times, I'm going to assume that we're talking about actually the equinox. When the sun does rise at exactly 6 a.m. and the sun does set at exactly 6 p.m. Now, the last thing to consider here, it's kind of a subtlety, but we divide the Earth into 24 different time zones. And everyone in, say, the central time zone is going to say it's noon at the same time. Even if, let's say us here in Minneapolis are directly along this line, and if it's noon for us, it's also going to be noon for someone in Chicago who might be a little bit offset from us. Or it might also be noon for someone in Lincoln, Nebraska, who might be offset from us. So within our time zones, the only person who this absolutely applies to is someone in the very center of the time zone. But again, that's a nuance. It's just a small correction. I'm not going to worry about that. We're going to talk about strictly solar time here, as if the only thing we could use to tell time was the sun and nothing else. Okay, so anyway, the reason this is important is that now I'm going to draw on top of this the orbit of the moon. Can I do this big enough? All right. I'm moving the whole thing over. All right, so I'm going to draw the whole orbit of the moon here. All right. And again, the sun is coming from over here. So, first of all, if it's going to be a new moon, the sun is coming from straight over here. Where does moon have to be? The moon, if it's a new moon, must be situated directly between us on the Earth and the sun, which is over in that direction. So the moon must be over here. Now, if the sun is on this side, it must be lighting up the left-hand side of the moon. Therefore, this is dark. And us here on Earth are going to be looking at the dark side of the moon. For sake of argument here, I'm going to be making this smaller. Okay. 1 second. All right. So the new moon is going to be overhead in this region of its orbit. Now, if we wait 1 week, the moon will have moved from that point in its orbit to right here. We know this as the first quarter moon. It's exactly 1/4 of the way through its orbit. So new moon, first quarter. Now, if we, sorry, that says first quarter down there, you can't see it. If we wait another week, exactly 1 more quarter of the orbit, the moon will be right here. And now it becomes pretty obvious that what we see as a full moon, there's a good reason for that, because the sun is shining from there, it's illuminating entirely the front side of the moon. That's also the side of the moon that we're seeing from the point of view of Earth. Now if we go around 1 more time, 1 more quarter, the moon gets up into the very top of the orbit here, and still the side of the moon that's facing the sun, the left side, is what's illuminated. So note that I haven't said anything about the times here quite yet. I will in a second. But again, we call this the last quarter phase. So this side, it's lit up on the left. This side, it's lit up on the right. The reason what we actually see is exactly swap from that is that we're actually, so here you're looking up, left, and right. As the Earth spins, we're looking downwards. So if we draw a guy right here, there's a gigantic person standing on the Earth. Now, if the person is standing like this, his left hand is over there. That's his left hand. And this is his right hand. So even though from our point of view out above the plane of the Earth, the moon is situated like that, this person here, that's his left side and that's his right side, when he looks up and he sees the moon, so that's his view, he's going to see the lit up side of the moon on his right side, and he's going to see the dark side of the moon on his left side. So his view will actually look exactly opposite what we've drawn there. That's his view of the third quarter moon, lit up on the first quarter moon, lit up on the right side. And that's exactly what we had said before. The first quarter, as well as any of the waxing phases, are going to be lit up on the right-hand side. Okay, so let's get rid of that. Okay, so hopefully this makes sense. Now just one more thing, by the way. Between new and first quarter, everything in between this section of the diagram is going to be what phase of the moon? A waxing crescent. Everything after first quarter, but before full, is going to be waxing gibbous. I'm just going to write abbreviations. Once it hits full, which by the way, I have to label that. Once it hits full, it's going to start getting smaller each night, so that's a waning gibbous because it's still more than half full. It's still more than half illuminated. And finally, in the very last part of the segment, when it hits last quarter and then it's getting smaller yet, it's a waning crescent. So we divided the moon's entire orbit into, first of all, the main key points, the new point in its orbit, first quarter, full, and last quarter. And then we divided everything else into segments waxing crescent, waxing gibbous, waning crescent. Now this is really important. If you understand this, everything really kind of makes sense from here. So I'm going to combine this, what we just talked about here, with the Earth clock that we drew a little bit earlier. So let's talk about a new moon here. The moon is right here in the orbit. It's in the new phase. Where on Earth would you have to be looking straight up at that new phase? The answer, of course, is right there. And we had already said that someone standing right here directly facing the sun will say it's noon. So the new moon is going to be highest in the sky at noon. There's a lot of new sounds there. But now let's go on the other side now. Let's talk about a full moon. What time of day is someone going to see the full moon directly overhead? So in this case, if you trace back from full, you'll see that someone has to be standing right here, directly opposite the sun, to see the full moon directly overhead. And we had said that's what time we call midnight. So the full moon is highest at midnight. This is why you can never see the full moon in the middle of the day. You can only ever see the full moon in the evening, in the dark hours. Now let's do the other two phases here. Let's do the first quarter. Now the first quarter, now this is a general way we do this here. To see when the moon is going to be highest, we simply just make a line straight from wherever the moon is in its orbit at that point. Wherever it hits the Earth, now you go back to your Earth clock diagram, and so you should all have the labeled tick marks on there. But this would exactly correspond with 6 p.m. So this first quarter phase, which by the way, September 12th, 2013, when I'm recording this, that's exactly what phase we have right now, first quarter. And so if you were to go out at about 6 p.m., that's when and actually 7 if we correct for daylight savings, that's when the moon is at the highest point in its orbit. And then finally, last quarter, remember this is 6 a.m. here, so someone who it's 6 a.m. for is going to see the last quarter moon at the highest point in its orbit. Okay, so let's see what phases someone, okay, so let's go to someone who it's 9 p.m. for. That's 9 p.m. right there, halfway between 6 p.m. and midnight. If it's 9 p.m. for you, what we can do is draw your horizon. So I'm basically going to draw the region that you could possibly see without the Earth obstructing your view. Everything up this way, sorry, let's do it this way. Everything in this direction, this direction, this direction, everything on this half of the sky, you can see at 9 p.m. So you can very clearly see if it's a waxing gibbous phase, no matter where it is between first quarter and full, that's going to appear more or less overhead, almost directly overhead for you at 9 p.m. At 9 p.m. you could also see the moon if it was in the full phase here. And you could even see the first few days of a waning gibbous at 9 p.m. You couldn't see it when it's at last quarter or when it's at like the day before last quarter or so, because you would have to literally look through the Earth to see that, and that's obviously not possible. That does not work. But if you can make a straight line from some point in the moon's orbit, say right there, to that 9 p.m. person, you can see it. So at 9 p.m. you could also look down and see the first quarter moon, and you could even look down and see the last few days of a waxing crescent moon. So you can play this game no matter where you are on the Earth. If you say it's 9 a.m., you could draw the person right there and then draw his horizon, and you can figure out which phases of the moon they could see. So in that case, it'd actually be the exact opposite of someone who it's 9 p.m. for. One more thing I want to mention about this, though. So let's say that I give you a random phase. Let's say the moon is right there in its orbit. If you want to see when that particular moon is going to be visible in the sky, so this would be a waning crescent, maybe a day or two, probably 2 days before it hits new moon phase. So if the moon is right here, the way to figure out when that's going to be visible in the sky is to do this. First, we make a line straight down to the Earth. And then we figure out if there is someone standing right here on the Earth, what time of day would they call it? So here, that's not quite halfway from 6 a.m. to noon. That's a little bit more than halfway, I would say. So if that's 9 a.m., I would say this is about 10 a.m. here. 9, 10, 11, noon. So I would say that this particular phase of waning crescent is going to be highest in the sky. How should I do this? I'm just going to erase a whole bunch of stuff here. This particular phase of waning crescent is going to be highest at 10 a.m. So here's the other thing. On average, the moon is in the sky for 12 hours of the day, and it's below your horizon the other 12 hours of the day. 12 hours above, 12 hours below. So let's say the moon's reached its highest point in the sky. Right here at 10 a.m., this waxing or waning gibbous moon is at the highest point it's going to be at in the sky. So if we assume that's going to be up for 12 hours, that means that it's already been in the sky for 6 hours. It rose and it spent 6 hours reaching its highest point, and then now it's going to spend another 6 hours setting. So the easy way to do this, to first order at least, to a rough approximation, if you know the moon was at its highest point at 10 a.m., it must have risen 6 hours before that. So that means the moon would rise. This particular phase of waning gibbous, waning crescent, must have risen 6 hours earlier, or 4 a.m., and it must set exactly 6 hours later, or you could say 16 a.m., that doesn't quite work. That's the same thing as 4 p.m. So a waning crescent moon at this point in its orbit, maybe just 2 days before new moon, is going to be in the sky all the way from 4 a.m., reaching the highest point at 10 a.m.,